Okay, worksheet 18, part 1. It's important to reference the following. It's off the internet. It's the Cup-Halt network analysis, chapter 10. This video will pertain to superposition, and then eventually the second one will probably have some Thevenin and Norton in it. A later video we're going to go over Millman's, I can tell you that, and we will do the delta y delta conversions also, as well as maximum power transfer theorem. We'll do an exercise on those. So chapter 10 is a good chapter to read all the way through, and that's a good place to start. Due to technical difficulties, my first video did not make, and I'm having to remake this one. So here we go. Superposition. Use superposition to determine the current flowing in a circuit with an AC 6-volt source. Now, 6 volts AC, 6V means RMS. If the author or the question had said VP, it would mean peak voltage. If it had said VPP here, where my mouse is, then that would be the peak to peak. But the fact that you just see a V means it is the RMS, and that's the convention that everyone uses. So I've got an AC 6-volt source, and the other thing about AC is usually you're given a frequency. If you're not, consider it to be 60 Hertz, because that's the most common frequency you'll see. At least that's my take on it. Other instructors may differ. So make sure you ask, if you don't see a frequency, what their policy is. So anyway, I'm describing a circuit 6.8 to a 2.7 to ground, and then between the 6.8 and 2.7 another wire is connected going through a 5.1K to a 10-volt DC source on the positive side. The negative side of the DC source is grounded. So the circuit looks like that. So my AC 6 volts, I've got my 6.8K resistor through my 2.7K resistor. Between these two, I've got another resistor that goes over to the positive side of my 10-volt DC source. Now, what we have not done in this class thus far is go in and set up an AC source, so I'm going to show you how to do that. When we set the voltage DC, let's cancel. When we set the voltage DC, we always set it here at DC value. We ignore the fact there's an advanced tab. If you push the advanced tab, you get this. One of the things about it, LT Spice, that we can do is they call it amplitude, and amplitude is really volts peak. But instead of converting this to a volts peak level, because I know it's RMS, I'm just going to use the 6 as my RMS, and I'm going to pretend this is RMS. Because if you put in peak, you get out peak voltages and peak currents. If you put in the RMS value, you get out the RMS voltages and the RMS currents, and that's usually what you want, because that's what your meter will read. Your multimeter will read the RMS level, not the peak. You have to have an oscilloscope to see the peak and the peak to peak. So even though this says amplitude, I'm going to put in 6 because it's 6 volts RMS. That's all I have to do. It's an AC source. Okay. So there we go. But the whole reason behind having to use superposition is this is frequency 60. This, being a DC source, is frequency 0. Their frequencies are different, therefore I cannot solve this circuit the way it is. I must use superposition because I have different frequencies. So basically what I've got to do is I've got to take this circuit, and if my circuit has a voltage source, I can remove the voltage source and short it. If it was to have a current source, then I would just take the current source out and leave the open in the circuit. So that's how you do it, and that will also show up in Thevenin and Norton as far as doing the Thevenin and Norton analysis, which we get to eventually. So if it's a voltage source and you want to remove it for some kind of analysis, you would short it. If it's a current source, you would leave it open, or you would leave it out of the circuit. So this circuit becomes two circuits. So the first one is the AC side, and what you see is this is the same circuit that you saw on the last page, and what I've got is I've got multiple circuits up here. So I redrew it, same values, everything's the same except there is no DC source here. Now that I have a 1 voltage source circuit, I can in fact solve it. So from an AC standpoint, I go in, set my amplitude, okay, and then on my analysis, to do AC analysis, simple AC analysis, I do AC analysis. We will use transient when we want to see something that looks like the waveforms on the oscilloscope. So for simple stuff we do this. When we want to see what it looks like on an oscilloscope, we have to use transient, and we'll get into that eventually. So I had to click on the AC analysis tab. I had to do the pull down list, and I want to make it a list, and my only frequency that I care about is the 60 Hertz frequency. And so when I've got list 60, you see that I am .AC analysis list 60, and then OK. That's my analysis. So it's a little more involved than the .OP, and then if I run it, what you see is you get your voltages. So I get a 6 volts AC between this point and ground. I get about 1.23 volts between this point and ground, so you know the voltage drops across each resistor, or can calculate them. And also what SPICE does is it tells you the current through each of the resistors. Now this is an AC current. So in order to answer 1 through 5, you need the voltage drop across these resistors, which the 2.7 and the 5.1 are going to have a 1.24 volt AC voltage drop. The 6.8 will be the difference between 6 and 1.23, whatever that is, 4, 7, something like that, 4.74, something like that. That will be the voltage drop, and then the current you have directly, and that will be the AC values across those components. And then you'll be halfway to your answer. Okay? So you will have this circuit part of the way solved, and then now you've got to find the DC values across these components. So what we do is we go in and remove the AC source. Same resistors, same configuration of resistors, but now I've got my AC. Now I have had students in the past who just change things around. You've got to respect where things are. In this circuit, the AC voltage source was removed and shorted. So there is a connection. And then my DC source is 10 volts. To do my analysis, I do my .op because I'm DC, and that's what we are used to doing. And then when I run it, I get my voltage values. Now, I did not label my nodes in either of these circuits, but I know that my 10 volt node is across my battery, and my 2.74 volt node is from here to ground. And it also tells me what my DC currents are. So the solution to problem 1 through 5 is, well, all this information, the voltage drops across each resistor, and you have to subtract 2.74 from 10 to get the voltage drop, the DC voltage drop across the 5.1K resistor. Okay? You know the DC current through all the resistors. I wouldn't worry about direction or anything. Just get numbers, and then as you gain experience with circuits, the numbers will sort of fall in place. You got AC values from this circuit, and so The solution to this circuit would be the combination of both the DC values and the AC values. And you could, in fact, build this circuit. And if you measured the AC voltage across the 6.8, you should get what you got in that circuit. You should get what you got in that circuit, etc. So you would see that the analysis works. Okay, so now I want to go back to the worksheet and use superposition. Solve the same circuit above 1 through 5 using two, let's make this DC sources because it will make it a little more easier, of identical frequency and in phase. So basically we're going to change the AC source to a DC source and then solve the circuit. And what you see is you can do this all as one circuit. If I change this to, got to get my spice tab back. If I change this to a DC 6 volts and this was a DC 10 volts and I did a dot op analysis, then I would get all my values. And the reason I can do that is because DC frequency is 0, this frequency is 0, the frequencies are the same. What I said in the original problem was to make this one an AC, this one a DC, make them both of the same frequency. And so if they're both the same frequency, AC, then the analysis that we did on this circuit would be the same. Whatever frequency they are the same, I could do that frequency and then I'd get all the values, even if I had another AC source over here. So that is what I want you to do. Just do a DC analysis. So you can see that superposition is one of those tools that you have that when you have to use it, you know how to use it, but when you don't have to use it, you also realize, hey, I don't have to use it. 8 through 11, solve the same circuit 1 through 5 using different frequencies of AC voltage, one at 100 hertz, one at 150. So you'd have to do two AC analysis on those circuits, and I'm going to say omit those or omit these problems. Now if you want to dabble in it, the more you dabble in this stuff, the better you'll get. So you would have to do it as two circuits. One at 100 hertz, one at 150 hertz. You'd have to get the 100 hertz values, you'd have to get the 150 hertz values, and then you would have to put them in a table together. This is probably where you would use like a transient, because you would see a really strange waveform when you start mixing AC signals, which is why I'm going to say omit these three, this 8 through 11. Okay, so after all this above, when must superposition be used? Superposition must be used when my frequencies are different. When can superposition be avoided? When my frequencies are the same. So if I've got an AC and a DC, definitely my frequencies are different because DC frequency is 0. And then I'll have an AC source which will have a frequency. So different frequencies, I got to break it into two parts. If I have two DC sources in a circuit, I don't have to use superposition. I can just use my analysis. Some classes teach superposition if you have more than one power supply, but if they're both DC, you don't need to do that. You can just solve it the way we've been doing it. If you're an AC and you're all at 60 hertz or 120 hertz or whatever hertz it is and everything's the same, you can also avoid it in AC circuits as long as the frequencies are identical. And that gets us through 12. Alright, I'm going to stop here and then go back and make a video for the second part. I got to do some setup. Thanks for watching.